In the previous lesson, we had taken a look at taking multiple vectors and adding them together into a resultant vector. However, sometimes the opposite is desired. Sometimes we want to take a single vector and do what is called resolve it into separate components. So we can read right here is what it says, is that it is often the case that we have a single force vector and we want to determine how much of the vector is acting in two separate directions. The most common case of this is resolving a vector into horizontal and vertical components, as illustrated by the example below. So let's go ahead and take a look at that example and see what we mean by that. So we've got on an XY coordinate plane, the X representing our horizontal, the Y representing the vertical. And we want to resolve this vector into its horizontal and vertical components. So what we're literally going to do, we're literally going to take and construct two right triangles where we have the horizontal component and then we have a vertical component. We could see from vector addition that the blue and red vectors that I just drew, if I were to take this red vector and move it over right here, that the blue and red added together would equal this force vector that has a magnitude of 45 pounds and is acting at an angle of 30 degrees above the horizontal. So resolving this vector into components, okay, into two separate vectors, and one in the horizontal, one in the vertical direction, we're essentially asking ourselves how much of this 45 pounds acts horizontally and how much acts vertically. To do that, in this case, since we're just looking at vertical and horizontal, is actually fairly straightforward from a trig standpoint because we've created two right triangles. So all it then takes is some basic trigonometry for us to be able to work through and figure out the results of this. So this first one, for the horizontal component, what I'm going to do is I'm going to draw the triangle that I have, and I know that the hypotenuse of this right triangle is 45, and that this angle here is 30 degrees. So if I want to find the horizontal component, that is this side length right here, all I need to do is use trigonometry. Well, here's my right angle, here's my hypotenuse. The angle measure that I know is adjacent, so that means I'm going to use the cosine. Cosine of theta is equal to adjacent over hypotenuse. So for us, that is cosine of 30 is equal to adjacent, which we're going to call x because we don't know what it is, x over our hypotenuse of 45. So the amount of the 45 pounds that is acting horizontally is simply x equals 45 times the cosine of 30. So if we work that out, go 45 times the cosine of 30, we end up with 38.97. Now I'm going to make sure really quick in mode that I am in degrees. If I'm in radians, it's going to give me something much different. I am in degrees, so I'm going to clear out so I can trust that calculation. So 38.97, I'm just going to say 39. We'll do 38.97. Okay, so x is equal to 38.97 pounds. So that's how much of the 45 pounds is acting in the horizontal direction. Well, fortunately, I can use the same triangle that I drew right here because this vertical piece is the same as this vertical piece I drew over here, because we had talked about this just being moved over here would be the same piece, the blue and the red together, added up to the 45. So for that case, instead of cosine, I'm going to use sine. So the sine of theta equals opposite, which is that vertical side over hypotenuse. So we end up with the sine of 30 is equal to, opposite, we'll call that y because we don't know what it is, over hypotenuse of 45. So y simply equals 45 times the sine of 30. So y is equal to 45 times the sine of 30. I believe the sine of 30 is a half, so this should be 22.5. And there it is, 22.5. So this 45 pounds acting at 30 degrees above the horizontal, we've now just determined that of that 45, 38.97 pounds of that are acting horizontally, and 22.5 pounds are acting vertically. Now you'll notice that these two numbers don't actually add up to each other, which we should actually expect because of the triangle we have here. To verify that these numbers are correct, it's not intuitive. We would think that it would be divided up so that these two components add to 45, but they don't, which is really interesting and actually pretty beneficial to us. But one way we can check is we can get our calculator, do some basic Pythagorean theorem. I'm going to go 38.97 squared plus 22.5 squared. And then I'm going to square root that number, or to the power of 0.5. And look what we get. We get just shy of 45 because the first number, the 38.97, was rounded a little bit. So in fact, those two do, through the Pythagorean theorem, add or result in that vector of 45. So there's the first example we can look at in relation to how to take a vector and decompose it and put it in its horizontal and vertical components. So what we want to do now, though, is to take a look at another situation that might be a little bit more involved, mainly because we're not looking at vertical and horizontal anymore. We're now looking at resolving a vector into two separate lines that not necessarily horizontal and vertical. So it says here this: the force F in figure 2.12 lies in the plane defined by the intersecting lines LA and LB. Its magnitude is 400. Okay, so there's a piece of information that I'm going to write down. 400 pounds. Okay, suppose that you want to resolve F into vector components parallel to LA and LB. So instead of parallel to a horizontal and vertical, we're parallel to two different lines. So we want to determine the magnitudes of the vector components graphically and by using trigonometry. Okay, so here's how we're going to approach this from a graphical perspective. The example we just did, we could do by drawing essentially a right triangle to show the component breakdown into the horizontal and vertical. But we're not dealing with horizontal and vertical here, so it's kind of hard to draw right triangles with this situation. So what we're going to do is we're going to follow what's called the parallelogram rule. What that means is this. These two lines, we're going to essentially have our force vector be the middle of a parallelogram. What I'm going to do is, following a line parallel to LB, I'm going to start at the tip of F and draw down to LA, noticing that those two are parallel to each other. What I'm going to do is I'm going to do the same thing here. So I've got this line right here, and I want to be parallel to that coming over to LB. So what you can see we've created here is essentially a parallelogram. But you can see that this force vector F is really made up of a vector acting along LB and a vector acting along LA. But if I take, you can see it two different ways. If I take this red vector and simply move it to right here, it's the same exact length and direction, and so the green and the red would add up to the blue. Or I could take this green vector here and move it up to this side of the parallelogram because it's parallel and the same length, and so the red plus the green would add up to the blue. What's nice is I now have a scenario that I can work with and really just use some trigonometry to figure it out. So again, the goal is to find the magnitude of the green and red pieces that F can be resolved into. So let's give those variable names. Since that's what we need to find. Let's call this. We'll just call this A, since it's along line A, and we'll call this B, since it's along line B. Now there's a couple things I can do. Because it's a parallelogram, my force vector F is acting as what's called a transversal, a line cutting two parallels. So from trigonometry, we know that alternate interior angles are equal to each other. So this right here is 60 degrees, just like that. Likewise, since this is 80, alternate interior are equal to each other. So we know some of that information. What's nice is, because of that, I can also figure out these two remaining angles, because I know the angles in a triangle add up to 180. So what I can do, 180 minus 80 minus 60, I'm left with 40 degrees for alpha. We can call that alpha if we want to, right down in here. So I know that this is now 40 degrees. The same thing is going to be true up here. What's nice about knowing all the angle measures is that now it's simply applying the law of sines in order to figure out A and B. Here's how I'm going to do it for A. Okay, I know that the sine, I'm going to do A, divided by the sine of its opposite angle, which we found was 60, is equal to any other side length. Well, I'm going to use this piece here because I know that it's 400. So 400 divided by the sine of its opposite angle, which is the 40. Excuse me. So if I work this math out, what I'm going to end up finding is that A is going to end up equaling 539 pounds. So what I would do is I would just multiply both sides by the sine of 60. Oh. So those cancel out, and A is equal to 400 times the sine of 60, all divided by the sine of 40. That gives you the 539. So for B, it's the same pattern, really. What I'm going to do is I'm going to do B divided by the sine of its opposite angle measure, which is 80. And that's equal to, again, that 400, because I know that side length, divided by the sine of its opposite angle. So that's the sine of 40. So in this case, multiply both sides by the sine of 80. When I work that out, I end up getting B is equal to 613 pounds. So I was able to successfully take this 400-pound force on this plane where LA and line A and line B were defining it. And with that, I was able to figure out that this 400 pounds, this is awkward because it's essentially saying that in order to do that, in order to get this 400 pounds acting in that direction, it takes 613 pounds acting in the B direction, and it takes 539 pounds acting in the A direction in order to accomplish that force vector of F equals 400 pounds in the direction that it is pointing. And what's interesting is both of those are greater than the 400 pounds. But hopefully you can see that because they're not perfectly horizontal or perpendicular to each other, they're almost opposing each other. And so both forces are actually greater each individually than the resultant because they're fighting against each other. And only part of each of A and B are actually working together to get that 400 pounds. So there's two examples of how to take a vector and resolve it into its components, whether it is into its horizontal and vertical, as in the first example, or into two defined lines of action, as in our second example. But as you can see in both cases, it simply falls down to setting up triangles and using trigonometry to solve for angles and side lengths.